Drawing inspiration from the architecture and processes of the human brain, neuromorphic computing relies on artificial neurons to carry out computations and mirror various neural activities such as perception, movement coordination, and the integration of multiple sensory inputs. Analog, digital, and combination VLSI designs bring these concepts to physical form, focusing on properties like resilience, adaptability, and the capacity for learning by distributing computation throughout numerous compact processing elements. This area draws from several fields including biology, mathematics, physics, computer science, and electronic engineering, to create systems that not only physically resemble the brain's structure, but also replicate its methods for managing information. The ambitions of neuromorphic computes focus on reducing energy consumption and expanding computational abilities to suit fields such as artificial intelligence, recognizing patterns, and analyzing sensory data. Early groundwork was established in the late 1980s when an initial proposition emerged, conceptualizing electronic systems with brain-like characteristics. Through the decades, milestones have accumulated. In 2006, a reconfigurable neural array built on silicon replicated qualities of neuronal ion channels. In 2011, work at MIT produced a chip with hundreds of transistors that simulated communication between synapses using well-established semiconductor processes. New models emerged frequently. In 2012, investigations at HP Labs highlighted the volatile properties of Mott memristors, which proved capable of mimicking aspects of neuronal operation and were posited as elements for computational machines. The same year, researchers at Purdue demonstrated a neuromorphic approach joining lateral spin valves with memristors. Large-scale, brain-inspired digital reconstructions arrived in 2013 with the detailed modeling of rodent brains. The following year, Stanford's NeuroGrid used several dedicated chips to emulate more than 60,000 neurons. Both corporate and public initiatives shaped recent advances projects supporting comprehensive exploratory efforts and the debut of new chips designed to simulate learning and inference far beyond classic computing paradigms. Efforts intensified in later years, such as a neuromorphic supercomputer in Heidelberg designed to operate much more quickly than natural neural tissues, and programmable chips developed at Intel capable of dynamic learning. Diverse examples reflect the wide-ranging investigation into materials and designs. A self-teaching chip crafted with resistive memory elements displayed creative potential through music learning, while recent approaches pursued even more realistic artificial synapses with proton conductors for deep learning applications. Investments from European entities have supported research blending neuromorphic strategies with quantum technologies, further emphasizing the flexible nature of this discipline. Studies at the Max Planck Institute extended these concepts through organic spiking neurons for direct interface with biological or environmental signals. Recent findings have suggested that chemical arrangements in fluids may serve as detectors for sound, hinting at emerging possibilities for computation inspired by biological systems. Neuromorphic engineering draws inspiration from how the brain organizes and executes information processing, integrating the analog characteristics of biological computation and investigating how neurons contribute to cognitive functions. Neurons in the brain communicate information through chemical signaling, a process that can be represented as mathematical operations. In neuromorphic systems, computation is distributed among numerous small, discrete units, reminiscent of neuronal components, guided by detailed neural maps and connection data compiled through techniques such as electron microscopy. These systems use specialized hardware, including devices like memristors composed of metal oxides, memory structures based on the electron spin properties known as spintronic memories, threshold-based electronic switches, and various transistor designs. Alongside hardware, spiking neural networks are trained using error-based learning approaches, adapting principles found in traditional neural network training to architectures inspired by biological neurons. Within this domain, neuromemristive systems adopt memristors to simulate the adaptive capabilities seen in neural pathways, capturing aspects of neuroplasticity. Rather than replicating the minute structural details of brain tissue, these systems prioritize abstractions, emphasizing the computational patterns of neural networks. Such architectures support pattern recognition tasks in areas like voice interpretation, facial analysis, and identifying objects, even substituting certain functions typically performed by digital logic gates. The evolving state of memory in memoristive systems is characterized by mathematical descriptions, such as the Caravelli-Traversa-di-Ventre relation, which offers insights into complex memory behaviors, including tunneling effects and stability criteria defined through Lyapunov methods. Neuromorphic design principles are also translated into sensory technology. Devices modeled to act like the retina, for instance, detect changes in light intensity at a local level. When these retinomorphic sensors operate in large arrays, they form event cameras capable of capturing scene dynamics by monitoring shifts in brightness, an approach that can reduce energy consumption by prioritizing relevant visual activity and filtering out static information.